Okay, so finish off this section. I've mentioned already in passing that there's another comparison test called the limit comparison test. And the problem with, maybe I shouldn't use that kind of language, but the problem with the comparison test is that to use it, you really need some intuition about what the series is doing. But then the comparison test doesn't let you directly use that intuition. So, we have whatever, we have this. And we look at this and we say, well, n is getting really big, n is going to infinity. And when we have a really big number, that square is going to blot out the negative n and the plus 1. I mean, we learned that all the way back in college algebra, when we learned that polynomials look like they're leading terms if you zoom out far enough. And then we say, well, 1 over n squared, this thing it looks like, converges. It's a p series, p equals 2. So this looks like a convergent series. It probably converges. But then to use the limit comparison, the regular comparison test, to show convergence, we have to take this and we have to finagle it until it is smaller than a finite series. And the intuition we have is no help at all in terms of actually doing that. I mean, we could figure this out with the comparison test, that if we want to make it bigger, we could get rid of the negative n, and we could do something to the 1. But the reality is that if we have this intuition, we'd rather use it. And the limit comparison test is a little less straightforward than the regular comparison test, but it lets you use your intuition directly. The limit comparison test says, suppose the limit as n goes to infinity of a sub n over b sub n is some positive number k. So this is a strict inequality. K can't be 0, k can't be infinity. Let me try to get that little mark out of there. Then the series a sub n and b sub n either both converge or they both diverge. And I guess I should say, just like the comparison test, and just like the integral test for that matter, we're assuming for now that these things we're adding are all positive. We'll learn a test that works with negative terms next week. So where this is coming from, it's coming from the observation that constant multiples don't change convergence. So the two series I have written on the board, A sub n and k times A sub n, these either both converge or they both diverge together. And of course, if we take that idea on the last frame, if we divide the terms of these series, they're equal to k. They're equal to a constant. And the limit comparison test is then a slight relaxation of this idea. You know, we've got, if this quotient is equal to k exactly, then we're in this situation and they either both converge or both diverge. We can strengthen this so that they don't have to be equal to k, they just have to approach k. And hence the limit in this test. And taking this idea, I keep saying that this test lets us use our intuition. So the intuition we're hopefully developing is that those two series should be similar when n is big. When n is close to infinity, the negative n and the plus one don't really do anything. And the limit comparison test lets us try to use this intuition directly. It says we think these terms and these terms are basically the same if we take a limit of their fractions and we get a positive finite number, then that is true. And they converge or they diverge together. We're going to be doing a lot with fractions of fractions. It's going to be a big thing when we get to the ratio test next week. So hopefully this is something we're comfortable with. We fit the denominator and we multiply top and bottom by it. Bottom cancels. We get an n squared up here. And then, I mean, we might just be able to do this because we're looking for, I mean, the limit as n goes to infinity is a horizontal asymptote, and we learn how to find horizontal asymptotes in college algebra, maybe. But if not, it's fine. This is infinity over infinity. We are hitting it with L'Hopital's rule a few times. The limit of 1 is 1, so we get 1. And 1 is a finite number, so the limit comparison test works. And the fact that this converges means that this also converges. Doing an example where we have divergence, I mean, let's do a few examples. 2n plus 1 over 6n squared minus 2n plus 3. I guess I can't really ask you whether you think this converges or not, since I already answered that, but polynomials look like they're leading terms as n gets big. So that linear expression looks like 2n And that quadratic expression looks like 6n squared so this thing starts to look more and more like 1 over n. And 1 over n is harmonic. The harmonic series diverges. This 1/3 isn't really hurting anything. It's not really doing anything. 1/3 of infinity is infinity. So we think it looks like the harmonic series, and the harmonic series diverges. That's sorry, I'm just looking at this and thinking, am I going to get the result I'm expecting here? But of course, the one nice thing about this test, you know, the test can work, it cannot work, but we don't have to sit around and worry about why isn't this giving me what I expect, though. I'm sure this looks like the harmonic series. I'm really confident it diverges, but oh yes, sorry, my mind is just going and just looking ahead at completely different tests. Everything is working out perfectly well here. Ignore all that hesitation. We take the 1 up, we flip this one over n, we get 2n squared plus n. And we get 6n squared minus 2n plus 3. And we're taking the limit as n goes to infinity. And we can use L'Hopital's rule twice. Possibly we can just look at this and say that the limit's going to be 1/3, but if not, it's fine. 4n plus 1, 12n minus 2. L'Hopital's rule a second time. So this is indeed 1/3. And again, there's the ratio test next week, and in the ratio test, you take a limit, and if you get a small number, it means the series converges, and those were getting messed up in my mind, and I was saying this series doesn't converge, it should diverge, and that's exactly what the limit comparison test tells us. The only thing this 1/3 means is that these series are similar. It's a finite number. They either both converge or they both diverge. So because the harmonic series diverges, the series on the left diverges. When I did the limit comparison test, because the only thing that matters is whether you get a finite number or not. I mean, I didn't really forget that 1/3. If I wanted to, I could have put it in. It would not have affected the outcome. outcome. We'd still have got enough finite limit, and they still both have converged or diverged together. Diverged in this case. So this is sort of, I mean, it's a little specialized in the sense that we have to sort of, I mean, we have to have some intuition about what's going on. It works really well when we have algebraic expressions, because algebraic expressions look like their highest power. And we can therefore use that for the comparison. That's what we did here. That's what we did in the first example. It's going to work well here, although we, to find the limit, we might need a derivative that we don't remember. But again, this works well when you have a very strong intuition that the series we're looking at is just a slightly more complicated version of another series. And we've said it works well for algebraic terms. It often works well when you have exponentials, because exponentials get so big so fast that we can often just ignore everything that isn't the exponential. I mean, 2 to the 100th power versus 100 is not even a competition. That 2 to the n is really important. That minus n is just kind of a detail. So this looks like 1 over 2 to the n. 1 over 2 to the n is geometric. It's not written quite like a geometric series, but we can rewrite it as 1/2 to the n. And 1/2 to the n converges. 1/2 is less than 1. So we say, well, this should look like 1 over 2 to the n, and 1 over 2 to the n converges. So the original series ought to converge. It looks like a convergent thing. And again, this test lets us directly use whatever intuition we might have. With the regular comparison test, we'd now be looking at this and saying, well, what do we do now? How do we make this bigger? Here, we can just directly compare the two with a limit and see what happens. And if the limit is a finite non-zero number, they both do the same thing. And here's the limit. This is L'Hopital's rule. The top and bottom are both going very quickly to infinity. It's probably an open question. I mean, we learned that the derivative of e to the x is e to the x, and then just sort of don't think about other bases. So I don't know if we remember how to take this derivative, but the derivative of a to the x, it's got a constant in it. It's got a natural log of a. Then we've got the exponential, a to the x. x. So e is special because the natural log of e is 1, and that constant goes away. Everything else, you have that natural log. Hit this with L'Hopital's rule. Hit it with L'Hopital's rule again. We'll just get a second natural log in the top and the bottom. -1 goes away when we take the derivative. I hope this is, this natural log of 2 is a constant. It just sits there. When we take this derivative, we get another natural log of 2. So that's why these natural log of 2s are now being squared. Everything cancels. This turns into 1. And the limit is 1, and 1 is a finite number. It is not 0, so these series either converge or diverge together. In this case, the geometric series converges. So this also converges. And let me see, it's going to be a slightly brief lecture, kind of only do so many of these. Let me look at one maybe slightly messier example, although not much messier. And put a 2 there. We can't start at 1. If we started at 1, we'd get the division by 0 error. So that's the only thing that 2 is doing. Well, what do we think? We've done a few problems like this by now. Let's take this piece by piece. As n is getting big, what's that n squared minus 1 looking like?
It's also getting bigger.
That's correct. But I mean, the intuition we have here, for example, is that when n is getting big, these polynomials are looking more and more like their leading term. So n squared minus 1 is looking more and more like what? Well, n squared minus 1 is a polynomial. If a polynomial is looking more and more like its leading term, what's the leading term of n squared minus 1?
N squared.
N squared. So this thing under the square root, that minus 1 isn't really doing much. It's starting to look more and more like n squared, the square root of n squared, bearing in mind that we're positive, that's n. So if we didn't have that minus 1, this would be convergent. If we didn't have this -1, this would just be a convergent p-series written a little weirdly. And we do have that -1, but again, you know, a Boolean -1 versus a Boolean. I mean, as n is getting big, this -1 is getting progressively less important. So, you know, as n is getting big, as we're going up to infinity, this should look basically like 1 over n squared. And let's see if we can, we might run out of space. I'll take the limit later. For now, let's just compare these and see how we can simplify them. There is a trick here, and it's a pretty standard trick. It's a trick you ought to know for like the homework. Well, the first thing that happens is that cancellation happens. That's not a trick. That's just a fact of math. N squared divided by n is n. The n squared cancels that n down there and becomes n itself. Now, here's the trick. This is, I mean, you don't strictly need to do this. You could hit this with L'Hopital's rule. It's infinity over infinity. But L'Hopital's rule is going to be kind of messy here because we have this square root and we have that thing inside the square root. When we use the take the derivative, we're going to have to use the chain rule. I'm instead going to take the argument. You know, I made the observation that the square root of n squared is n. And I'm going to go in reverse. And the reason that I'm doing this is that you might think, okay, now L'Hopital's rule will be even worse because now I'll have square roots and the chain rule in the top and the bottom. But we're going to use a fact from algebra, which is that the square root, which is that the limit of a square root is the square root of the limit. So actually, we're going to get around messing with these square roots at all. The square root of n squared over the square root of n squared minus 1. A square root divided by a square root can be rewritten as a single square root and we can take the limit inside a square root. And now L'Hopital's rule, or maybe you don't need L'Hopital's rule. Maybe you just look at this and you say, well, the degrees are equal, so we divide the leading terms. And if we hit this with L'Hopital's rule, we get 2n and 2n. The square root of 1. The limit as of n squared over n squared minus 1 is 1. We take that limit, we get 1. We get the square root of 1, which is 1. So again, we have this. This rule can fail in the sense that it's, to use this rule, well, first it can fail on a human level. I mean, we need intuition about what the series looks like. If we, and we need intuition that it looks like a series we know converges or we know diverges. But also, it can be that you take the limit and you get not a finite non-zero number. And this rule can be extended a little, but basically if that happens, the rule's failed and you have to try something else. Like, I don't know, say you have 1 over the natural logarithm of n. And you want to know if this converges or diverges. This is actually a really good candidate for the regular comparison test, but we look at this and we say natural log of n. Well, I don't know, man. I mean, the natural log of n's really slow growing. I guess the next slowest growing function we have are linear expressions. So if it's going to look like anything, it's probably going to look like 1 over n. So with that kind of dubious intuition, we proceed. Am I about to make a fool of myself? Is this going to work perfectly? We'll find out in a second. So this is n over, and nope, I'm not. This is going to fail. This is n over the natural log of n. This is going to infinity. We're reaching the point in our mathematical career where maybe ideally you're starting to sort of see that. You're starting to say, well, the natural log is growing really, really slowly. Like the natural log of a big number is much smaller than that number. So, I mean, you have a number here that's getting big. You have a number here that's growing really, really slowly. If the numerator is getting bigger than the denominator, the whole thing is going to infinity. Is the logic we might have, but if we don't have that logic, fortunately, L'Hopital's rule works just fine. The derivative of n is 1. The derivative of the natural log is 1 over n. The limit as n goes to infinity of n equals infinity. And this is, you can call it, I mean, the rule isn't failing exactly. The rule is telling you that your intuition is bad, that this series up here and this series over here are actually quite different and they don't converge or diverge together. So it's not exactly that the rule is failing, but we have failed to use it. We have not found a series that we can limit compare 1 over the natural log of n to. And they say it doesn't happen that often, but occasionally you do get a rule that's crying out for the regular comparison test. Because the natural log is so slow growing, the natural log of n is less than n, meaning 1 over the natural log of n is greater than 1 over n. Well, 1 over n is the harmonic series. It goes to infinity, meaning that this bigger series also goes to infinity. So it diverges by the regular comparison test. And natural logs in general can be hard to deal with. Trig functions too. You'll notice we haven't been doing a bunch of examples with trig functions. So that's it for this week. Didn't end as early as I was afraid of. Next week, we're going to really get into this. Next week, we're going to use the ratio test, and that's the major one. When we start looking at applications of infinite series, the ratio test is the test we use in a sort of day-to-day basis. So, you know, the material we've been looking at is maybe interesting and it's part of the standard curriculum, but in the next week, we'll look at sort of our bread and butter technique. And I will see you then.